Yep. Yeah, thank you, Silvio, Islam, all other people in the organizing committee for the kind invitation, and in particular also for all the friendship over the past so many years. Yes, you have a picture on the left from my PhD defense and a more recent one yesterday. So in my talk, I will start with some kind of preliminary results. Then I will make a short story about several topics. Maybe it may be a bit chaotic in the beginning, but the idea is that all puzzle pieces find their way to something more sound at the end. And then in the second part of my talk, I will talk about controller-induced reduction methods. One well-known technique and another one maybe less well-known one. And eventually I will end up with fixed time and prescribed time controller design. And at the end, I will touch applications in vibration control. Maybe to start with, so you have here the title. Maybe try to remember the keywords in the title because they will come back later on several times. Okay, the basics of time delay systems also maybe I should say this before. I will try to keep things as easy as possible, just to focus on very basic ideas. And my aim is also to try to connect with things many of you are doing, because I know it's a quite diverse audience. So I will try to touch several directions of research. So in the time, the very basics are if you have an ordinary differential equation, to define a trajectory, a forward trajectory, you need an initial condition, a vector, the function value at a given initial time step. For a time delay system, you need a function segment, a piece of trajectory. And in fact, the natural state, in the sense of the minimal information you need to define the future, it's like a piece of the trajectory, which you see when you take a window and you slide a window along your solution. What you see inside the window, that's the intuitive notion of a state. And this has given rise to many strongly connected representations, like an abstract ODE over a function space, or also PDE representations. So in the simulation below, you see in fact the characteristics very clearly of an advection PDE and transport equation. Pure transport with a constant speed, that's basically a delay. Then one of the key words, it's about small solutions. Okay, what's a small solution? Let's give an example. You take a system there, two equations, and you see for the initial state condition, you need a function segment for x1, x2, and you need x1 at the initial time. And now you take a function segment for x2, phi 2, such that the integral from minus tau to 0 is equal to 0. So now let's define the forward solution. So what will you see now? Okay, you start integrating x2, you start integrating the function segment. When you're at the end, you arrive at 0, and then you will continue at 0. That's a so-called small solution. The definition, a solution that decays to 0 faster than any exponential function. And in the linear time invariant case, it means that you reach 0 in a finite time. And this also makes clear that for delay equations, you cannot continue backward in time. Here you cannot even observe the initial condition, because if you start from 0 at a higher moment of time, you go back in time, you can arrive at infinitely many initial conditions. So you cannot go backward in time. So many people think about delay systems with memory, but you can also have some kind of fading memory. So you forget about, in this case, you forget about the initial condition. I come back to this later on in half an hour, I guess. Lissajous curves. Who's familiar with that? Raise your hand. Who has heard about Lissajous curves? I guess everyone. So what do we do in the plot? On top, I plot the sinus of omega tau 2 versus the sinus of omega tau 1. So omega, it's for the moment the time, a parameter. Think about time. And for the tau 1, tau 2, think about frequencies. So when the second frequency is it's the double of the first, you get a beautiful line 8. And in the figure to the right, you see just the argument of the sine function, modulo 2 pi. So what's now happening if you change the frequency tau 2 to 1.9? Then you will not have a beautiful 8 like in one cycle of the first case, but you will almost close. This can be very well seen to the right. The slope will be a little bit less, and then you end up not in the corner, but you will end a little bit lower. And then you will continue from the left, it's modulo 2 pi, and then you go and you follow the second line. So at the end, you have a periodic pattern, but you fill up the square better and better. And what's now happening? When you take the ratio, an irrational number of tau 2 and tau 1, then you will at the end you will not have periodicity, and you will densely fill out the whole square. Mathematically, you have exponentials, omega tau 1, tau 2, tau m. You take the union for all omega. What's happening? So of course, this will be a set which is part of the Cartesian products of unit circles. But when the delays are rationally independent, then the closure of that set will be actually not part of the union of the Cartesian products of unit circles, but it will be actually the complete set. So you densely fill up everything. And it's also something important, for instance, in the context of numerical integration using so-called lattice rules. So for tau 2 over tau 1, the square root of 2, you get a so-called low discrepancy sequence, which means that you fill up the square in an optimal way. What has this to do with time delay systems? Does any of you have an idea? I used tau 1, tau 2 for frequency, it's a bit unusual. That's a connection, but anything else? At least I will come back to it 5 times in my presentation. It's everywhere. And maybe all concepts related to strong stability, strong H2 norm, improperly posed problems, it's all related to Lissajous figures in some way. And by the way, about the picture, maybe the people that are not that are of my age, maybe you know that in the 1980s you had action heroes, Sylvester Stallone, you had Arnold Schwarzenegger, but you also had Jean-Claude Van Damme, with the nickname Muscles from Brussels. But unfortunately, he did not give me permission to use his picture, so I had to find for a substitute. Now I start my journey about different topics, and maybe stability regions in stability charts in delay spaces. So we have linear equations, 2 delays, and you visualize so-called stability crossing curves. And I indicated the stability region. And there was one issue that intrigued me, that in some directions you have holes. So you see, in one direction you don't have any intersection. That means that you have delay independent stability in a direction, but if you perturb the direction, then you have intersections. And this is something which intrigued me. I looked at it. It was in fact a mathematical result. A direction, you parameterize it by numbers R1, R2, or n. It's the direction of the beam through the origin. And you have delay independent stability if and only if this curve, a set of curves, does not intersect with the right half plane. And the curve, it's parameterized by omega, and the frequencies are determined by the direction. And of course, if you now make the delays rationally, the directional components rationally independent, this curve will go to some, we will coincide with some bigger set. But maybe let's just give the idea. I take direction 1 and 2, which I call strong resonance, a strong delay logging. For R1, R2, 1, 2, you have the curve I talked about, it's the red one. It's in the left half plane, so we have delay independent stability in that direction. But now I perturb the direction a little bit, and what will happen? The curve will not be periodic anymore with the same period, but with a bigger period, and you start to densely fill up the donut. So I hope you had good breakfast. If not, you have a donut on the screen. And you see, the donut intersects with the right half plane, so you lose delay independent stability. And of course, if you take any direction with an irrational slope, you always fill up the whole donut. Now, in practice, what's often happens that the donut is much more to the right, which means in fact that you will only have delay independent stability in a direction for so-called strong resonances. So R2 equal to R1, R2 equal to 2 times to R1, and so forth and so on. So a first connection with Lissajous curves. Now, the second topic, algebraic design approaches. In the last years in the group we've been working on solving a lot of control problems using algebraic methods. And many of them are connected explicitly or implicitly with the so-called normal form. Yeah? And then I just want to make clear here that it's not so, there are some challenges. And for the first one, I take a system with state delay and I make it easy. No delay in the input, no delay in the output, only state delay. And I look for the transfer function, and you see from the shape that you have a relative degree equal to 4. So you need to differentiate 4 times the output to have a connection with the input. But you see already something special. You have a delay, an exponential in the coefficient, even though we do not have any delay in the input or output. But now I do the following. Suppose that I'm not sure about the delays, 1, 2, 3. So I just call them tau 1, tau 2, tau 3. And I'm now looking for the transfer function. And what do you see now? Oops. I now see an extra term appearing. And when twice the second delay is not equal to the sum of tau 1 plus tau 2, for instance, when you have not 1, 2, and 3, we perturb it, you have a term appearing, and the relative degree goes from 4 till 3, which is a bit dangerous for some control design problems. So it may be sensitive to infinitesimal delay changes. And of course, if you have a matrix, if you replace 0 by non-zero, you create a new physical connection. It's logical that it can affect the relative degree, but now we only perturb state delays, and it has a huge effect. So, and now if you now look at the coefficient that suddenly appears, if you look at it on the imaginary axis, you get a function that uniformly converges to 0 on a compact compact omega interval. But if you allow omega to be very big, and if you allow perturbations on the delay, then you see again that all these exponentials, they will behave de facto as independent numbers. And what's in fact the conclusion from that thing in our studies? Okay, if the delays stem from different physical parameters, you must study all properties by looking at the viewpoint of the equation as an evolution equation on a ring of multivariate polynomials. And a very important comment I would like to make is, in practice, rationally independent delays, they are very, very important. Often I get the comment, but in practice you have digital things, all numbers on the digital implementation, they are commensurate by definition. No, but what's in fact the important point, if you look at the relative degree, it goes from 4 to 3. You don't have to make the delays rationally independent. It's sufficient to break my apologies, the strong resonance, that connection you have here. And another indication is that think about our Lissajous curves. You have delays 1 and 2 to the left, 1.9 and 2, or 1 and 1.9 to the right, even though they are still commensurate, but now they are 10 and 19 times basic delays. 10 and 19 are quite high, and you already fill up quite well the whole square, which means in fact that you're closer to the setting of rationally independent delays than to the setting of commensurate delays with relatively high basic delays. So in practice, it's important to look at multivariate polynomials. Another interesting thing I want to look at that makes the thing challenges. Okay, maybe just above you have the following result, which we proved recently. So if the coupling matrix, so if you take output derivatives, you couple them until you have a connection with the input. If the coupling matrix is unimodular, invertible over the ring of m-variate polynomials, then we can indeed construct a normal form, which is written there to the right, and where you have to replace at the end the ci by a delay operator to go back to the original description. But the same example from above also makes another challenge clear. I take the same example, and I take now particular values of the delay. So what may happen in practice is that the leading coefficient has a big delay, a non-leading a smaller delay. And that means, in fact, that if you look at invariant systems, you get this kind of advanced dynamics. So you can have infinitely many zeros in the right half plane that spread out to the right. And of course, this kind of behavior cannot be realized by a causal zero dynamics subsystem. So be a bit careful with this kind of analysis. It's quite challenging. And I will again move to a next topic. But as I said, at the end, everything will come back beautifully, I hope. Control design methods. So a lot of the things we have been doing from a computational side has been implemented in a software package, TDS control. And what's the setting? The typical H infinity robust control setting. We have on top a plant. It can be retarded, neutral type with discrete delays everywhere, inputs, output states. And what's the functionality? It designs static and dynamic output feedback controllers. And the typical routines include model reduction, also things for stabilization and for optimizing H infinity criteria. But now, if you look at this thing here, we take the so-called direct optimization approach. What does it mean? It's computationally oriented, so we directly optimize criteria as a function of parameters. So the parameter P is just a parameterization of the static or dynamic controller. And we optimize in looking for stabilizing controllers to minimize the spectral abscissa, the real part of the rightmost characteristic roots. And when with the neutral case, the supremum of the real parts of the characteristic roots. And then subsequently, we can use that as starting point to optimize H infinity criteria. We can add weight functions and so forth and so on. But now, how do we compute these things? We combine two things. Spectral methods for PDEs, linear algebra, it relates to the talk of Dimitri Breda yesterday. But we also use and extended tools for non-smooth optimization. And then maybe I try to shed light, why do we need non-smooth optimization? So look at the picture to the right. Suppose that we have one to the left, top left, sorry. We have one parameter. I change the parameter, what may happen? One eigenvalue moves to the left, so the real part is decreasing. Another one moves to the right, or a pair moves to the right, the real part is increasing. If you look at the maximum of the two, you get this kind of V shape. It can also happen that when you move a root to the left, it intersects with another one, you get a double non-semi-simple, you get even non-Lissajous behavior. And you see that this can happen in an optimum. What does it mean? You cannot use most tools for nonlinear programming, for solving nonlinear programs. Why not? Because most of them they rely on solving KKT conditions. KKT conditions in one parameter, derivative 0, you see that you don't have a derivative, only subdifferential. You even do not have Lissajous continuity. What's now the scenario in 2D? We get surfaces, and we get here some kind of intersection. What's in fact happening? So I have here my didactic material with two parameters. In practice, much more, of course. This is the real part of eigenvalue number 1, or pair number 1. This is the real part of pair number 2. And, and here they have the same real part, they coincide. So what's now happening, if you start to optimize it, you start here, and you go to the ridge, and then you need to follow the ridge if you do some kind of steepest descent, which means in fact that you have really to take into account non-smoothness here. But we have algorithms that can cope with that. And if you look at what's in fact happening here, you go here, you go there. This has to do with some kind of randomization in the algorithms. And at the end, we end up here. And in this case, it's a so-called Clark stationary point that corresponds to the optimum. What's in fact the whole idea? At some moment, you get a third surface that plays a role, and we find an optimizer here in this point. And on the top left figure, you see the corresponding sketch of how level sets look qualitatively. What's the connection with the picture above? So I'm trying to prepare you for the lunch session. So if you go to a fries shop in Belgium and you ask fries, French fries, then you get this kind of package. It's exactly this kind of structure filled with fries and some mayonnaise on top of it. By the way, the Belgian national dish is called French fries. You see, we're a bit very humble. So the French, they may not have stolen our election, but at least they stole our national dish. And now you see things in action. Optimization of the spectral abscissa, what do we essentially do? You have here the spectrum, and you start pushing the spectrum, and you try to push it to the left, hopefully to end up in a situation where all roots are in the left half plane. So here you did the spectrum, so it's pushed a bit to the left, and here also. And here you see another example before and after optimization. It's in fact an example from a PDE system, a laser physics problem described by a PDE with delay. And by the way, for the H-infinity synthesis problem, it's in fact exactly the same idea. Once that thing is stable, infinite norms exist, you get a frequency response with peaks. And instead of pushing everything to the left, you try to push all these peaks down. In the beginning, you push one peak down, then a second comes up, then you try to push two peaks down, and it's exactly the same phenomena, and you can use the same kind of tools. Another specific thing about the software that is in fact we use, it's all based on delay differential algebraic equation models. The leading matrix is singular. So not every equation is a differential equation. And in fact, the whole approach is based on the behavior approach in systems theory, that you just look at signals. And it's extremely powerful to model interconnected systems. Like examples Thomas has shown yesterday. You see, I add a system to my model. So you add a dynamical system, you add a differential equation. Another subsystem, dynamic, you add a differential equation. You couple them, you add an algebraic equation. Yes, you couple them with some delay, so you add a delay difference equation. So it's very flexible, and we developed these models in the framework of a European project about control of complex systems, so where network systems played a major role. Another flexibility, I talked about static and dynamic output feedback controls that can be synthesized, but by combination of the DDAE framework and the fact that we can impose structure sparsity on the controller, this allows to extend the scope a lot. Just suppose that we have a system, we want to design a PID controller. So what do we now do? You need Y for feedback, but you also need Y dot. So what do we do here? Title, slack variable. I just define a second equation. I define a new variable and say that the new variable is equal to Cx dot. That's Y dot. So the new output actually contains Y and Y dot. Of course, the leading matrix is singular, but we can handle that, no problem. And the second thing, we need a PID, we need the I. Yeah, we simply can automatically impose the fact that the A matrix of the controller should be equal to 0. So by sparsity and slack variables, you can automatically design a PID controller if you like. Another example, now many people are working on delay-based controllers. Suppose that you do not want to use Y for feedback, but a combination of Y at different time instants. There are many good motivations to do that. Now, if you look at the automatic remodeling, the second equation that's in fact the behavioral approach in action. You just have a relation between signals, the Y and the X, the output equation. But now I can add a slack variable equal to a delayed value of the output. So this is my big DDAE with matrix to the left, identity 0 and 0. And now if you do just standard out feedback of the generalized output, you're actually computing K1, Km, you're in fact synthesizing the controller above. Another example, which is shown below. Suppose that you have a network and you want to design a decentralized distributed controller. How can you view at a decentralized controller? So if you collect for the simplistic static controller, you collect all outputs, you collect all inputs, and you design one big matrix K, one gain, that's a centralized controller. But since we can automatically impose sparsity, so you can make sure that you end up with a controller that you can implement decentralized. So with the pattern below, we just take into account that every local controller has access to the own output and the output of a neighbor. And that structure is visualized in the left. So you can do a lot by imposing sparsity structure on your controller and working with slack variables in the DDAE framework. And then another thing, a final issue I want to highlight, we also take into account fragility problems. Suppose that we have this system model on top. You have an output, maybe a bit like an artificial description, just to sketch the main idea. I want to synthesize a output feedback controller, 3 parameters. Without control, it's unstable. And after the design, we get this kind of closed loop spectrum. Stable now, has been stabilized, but now we find a rightmost root with multiplicity 3 as rightmost point of the spectrum. Okay, it can be logical, but on the other hand, maybe you feel a bit like it's a bit strange. Yeah? Why? Because you have 3 degrees of freedom, 3 para K1, K2, K3, you have 3 rightmost roots, maybe, why can we not shift it to the left? And indeed, you can shift it more to the left if you like. But now, I perturb the delay a little bit, and now we get this picture. That beautiful chain, if you perturb the delays, it will start bending to the right. And at very high frequencies, it will bend back at the location of the triple root. And if you make the perturbation of the delay smaller, what will happen? The turning back will appear at higher frequencies. So actually we have 3 parameters, but we have 4 conflicting conditions. We have 3 roots which you want to go to the left, but we also take into account the behavior of the high frequency roots when you allow small delay perturbations. So we will take into account finite roots, but also what's happening at the point of infinity or perturbations of it when they come back. And maybe let's now just sketch the whole idea. What's in fact the problem? U depends on Y, and Y depends on U in the past. So you get an algebraic loop that transmits signals at very high frequencies. It's not a filter, it transmits everything. What's now happening? This is in fact for the people who know more about this kind of topics. This is in fact the delay difference equation associated with the closed loop system, which is of a neutral type. Now we're looking for a candidate root to sketch the idea. So I fill in, I substitute R plus I omega. So I'm looking for a root, you fill it in the equation. And then you look at all solutions and you project on the R axis. And then you get the real parts. And what do you now see in the equation? What is appearing there? Of course, the R. But you also get e to the power I omega tau 1, e to the power I omega tau 2. So when tau 1, tau 2 are 1 or 2.5 and 5, then the second exponential, it's equal to the square of the first. You're very tightly locked. You only have one independent parameter omega. But if you allow perturbations, like for our Lissajous curves, when you change tau 2 a little bit, you get frequency tau 1, tau 2. You're more independent, so you start to fill up the whole square, which in fact means that these two exponents de facto behave as independent variables. It allows you to enlarge the set a lot, leading to this kind of dancing. In fact, I planned to make some kind of video, but I did unfortunately not have time, where I changed the delay a little bit, and then I let the high frequency root dance around. So you can actually do that. And then maybe this also makes clear that in the software, we not only use the linear algebra kind of tools, but we also implemented algebraic approaches based on multivariate polynomials that analyze what's happening at infinity. And this can also happen in the context of H-infinity control. We have here a transfer matrix with, this is the frequency response. And the computed value of the H-infinity number is in fact the red thing here. You see, oh, it's not correct, you have a gap. But indeed, when you make a small delay perturbation, you can close the gap. So we take into account what can happen at very high frequencies, which is relevant and for neutral equations, DDAEs, and so forth and so on. All right. So this brings me to the second part of my talk about reduction methods. So I'm a bit very tired by pushing all eigenvalues to the left. It's very tiring with this kind of weather. Happily, we have air conditioning in this room, so I will still stay here the whole day. It's very nice. But anyway, so suppose now that we have a very particular structure delay in the input. Then we can increase performance a lot by prediction. What's the whole idea? You have a delay in the input. Suppose that the delay is shifted to the input. And you have an undelayed part in the dynamics. So you know, of course, the input up to the current time tau. So you know the input of the undelayed part till time t plus tau. So if you measure the current state, you can predict x over one time. And when you use the prediction of the state for feedback, you have in some sense eliminated the delay. This is known in the literature under different names. Predictor feedback, infinite dimensional backstepping, the Artstein transformation in the linear time invariant case. These are static schemes where we have to compute the prediction online. We also have dynamic schemes like the Smith predictor. I will not say much about it. I can only say you're very good in enhancing performance, but of course, robustness is important, in particular when you have instability and the prediction horizon is big. So I have here an example here, the most easy example, a stable system, Smith predictor. Below you have the delay in the blend, and on top you have the delay in the mathematical model. So when there is a delay mismatch, you can, my apologies, you can have instability. And what you see, of course, the absolute margin you have is more or less constant, but the relative degree margin, so if you take it into account the size of the nominal delay, it goes to 0. So prediction becomes more difficult when you have higher delays. And this is again an example of the Lissajous and what's all behind. This is now a very strong resonance where the second delay is equal to the first one. But you see there are also other of these stable ways. Now I'm going to talk about something else. A predictor, it's too complex for myself. Let's now do the following. The idea of act and wait proposed by Thomas Insberg and Gabor Stepan already some time ago. We take state feedback and we switch it on and off, on and off, on and off. So in a stationary phase, you move from an ODE description, no control, and a delayed description when the control is active. What's now the idea behind the reduction? In the beginning of the ODE phase, the whole solution is generated by the state at one time instant, by one point or one vector. Then you move to the delayed description. You need a history function, but the history function has been generated by the ODE. So in other words, the ODE determines the red thing, and the red thing is used as history for the delayed part. It means that the whole future is defined only by one point in this case. And that means, in fact, that the monodromy operator that maps over one period, it's essentially finite dimensional. And the relevant dynamics can be described by a matrix mapping. Yeah, it's my apologies for my pointer. So it's mapping one point onto the point one cycle before, and it has this kind of loop here. So you can reduce an infinite dimensional operator essentially to a finite dimensional one. And now, yeah, pole placement, this is going good because now we have in your K, we have n degrees of freedom, K1, Kn, and we have an n by n matrix. So maybe we can try to assign the spectrum of that monodromy matrix. And in this case, even YPIA number 2 maybe we should do the Mexican wave at the end of the talk, we even have a smooth formulation in terms of traces. So we don't need non-smooth optimization techniques anymore. And there's also potential for fixed time stability. Suppose now that I'm able to assign all eigenvalues of delta to 0. And that matrix becomes nilpotent. Nilpotent means that some power will be equal to 0. That means that all trajectories collapse into 0 in a finite time. And indeed, for the multiple integrator shown on top, this is in fact the case here. So you take a trajectory and all of them, they collapse into 0 exactly in a fixed time. And now just to talk a bit about this non-standard stability notion, the classical thing, asymptotic stability, error plots are shown on the top plot. It's a log scale. You then get error 10 to the power minus 1, minus 2, minus 3, minus 4, asymptotic stability. What is then finite time stability? What you can typically reach with sliding mode control laws based on homogeneity with square roots. It means that you reach 0 in a finite time, but it may depend on the initial condition. So the convergence time depends on how far you are from the equilibrium. But now we can achieve fixed time stability, which means that the convergence time is independent of the initial condition, which is in fact a very strong notion of stability. But of course, what about limitations induced by delay? No switching, U is k times x, you get infinitely many roots, finite number of parameters, you have problems, you have to push them, and at some moment you cannot handle everything. What's now in this case, it seems in fact quite easy. N equations into n unknowns. But of course you have the law of preservation of misery. The equations are polynomial, non-linear. And polynomial equations, they are very nasty. It's very hard to get a glimpse on solvability. And typically, preservation of misery, maybe in difficult cases, it might be that you cannot find a solution of these equations. And for that, my friend Bin-Shu came with a very simple idea, a very clever idea. Usually good ideas are simple, the following. Well. Let's now take in the off controller, it switches on and off, on and off, on and off. But let's now take a time varying gain in the on phase. Instead of a constant is something that can vary in time. So I replace k by k of t, and then the rest is not important. And now your delta will depend on some k. I only have to add bracket s. It depends on the time. And now, if you look at the equation, we do the following. We do some kind of completion. RH, I just add here a function of the size of the input. I discuss it later on. You add B transpose, an exponential. And what I'm building up is in fact a scaled version of a controllability Gramian. And then I add some matrix called Q. What's now the interesting stuff? That if A, B is controllable, that matrix in blue is invertible. And that means in fact that by playing with Q, you can assign delta as you wish. So now you can fully assign the whole monodromy operator, and you can also fully assign it to 0. And then what's now the role of that function RH? This is in fact smoother, because you can now do the following. With RH, you can smoothen the transitions, and you can even make sure that the gain which is on and off, that it will be infinitely many times differentiable everywhere. Not real analytic, but you can make it differentiable infinitely many times everywhere. And it means that, in fact, instead of a switched control law, on, off, you move to a nice policy-like control law. And indeed, we can assign the whole matrix delta to 0. So you just take the smoother, you compute that scaled controllability Gramian, you determine your Q in such a way that delta becomes 0. And that means all solutions converge to 0 in a finite time, 3 times the delay. The gains are bounded. Any degree of smoothness can be assumed. We do not need sliding modes. We do not need square roots in the control law. In theory, we have no restrictions on the delay, on the degree of instability of the matrix. In theory, you can achieve this kind of stability. So bound smooth feedback, and you have fixed time stability, independent of the initial condition, with the convergence time, which does not depend on the initial condition. And now again, I have a question for you. Do you think this is is there something a bit dangerous about the control? It's like switched on, off, on, off. Of course, you can also interpret it as Gabor once explained to me. It's like you observe and you act, you observe, you act, you observe, you act. But of course, in some application, you can imagine that on, off, it's not maybe the most important. If you have very fast, if you are driving a car at a high speed, you cannot say, I control and I fix my steering wheel. I control and I switch. But therefore, but I think, in my feeling, we have to face this. I think the important thing is that you can add them to improve controllers for systems without delay. And let's illustrate this by means of observation. I have on top the simplest linear system, and I want to build an observer. The way we teach it in school is typical. You take a copy of the dynamics, and you add an output injection term, the classical Lüneberger observer you have here. But now I add a second term, and that's the one I discussed before, with the gain switching on and off periodically. And now, the difference is that now the H, it's now a controller parameter. You can choose that you can play with H. And now we look at the observation error, and what do you see? The classical error dynamics, but with one extra term added. And what's now the interesting thing? The interesting thing, yeah, I cannot see it there. I wanted to interact with you, but I cannot see what I'm doing. So, I hope you're well. So what's in fact now the interesting things? If we look at it, the red thing switches on and off, on and off. But if we are in an off phase, we still have stable dynamics because of the first term we have here. And what's now the whole thing here? Because we can choose H, we can achieve prescribed time convergence in time 2H, and we can choose 2H induced by the second term. And we don't have any problems with open loop dynamics because we have the first output injection term, the classical one. And now maybe just what's in fact in summary. You have the actual state, and you have the state of the observer. When you're close together, suppose that you have small perturbations. The first term, what happens again? Oops, I did it again. Britney Spears. So what's happening now? If you have a small perturbations, the first blue term will keep things together, the classical term. But if you have a big perturbation, what will now happen? The second term will become active and make sure that in time 2h, two things are brought together in a prescribed time. And then the other term can take it up. And now some discussion about that. The ID sketch is at the basis of new work about fixed time, prescribed time control using smooth feedback laws. No sliding modes, no square roots, we don't need them. Keyword small, what do we do? In fact, we make sure by choosing the controller, we induce small solutions. By choice of the feedback, we make sure that all trajectories converge to zero and become so-called small solutions in a finite time. And we can close another loop with the introduction. And finally, this also fits within the scope of many recent works about intentional use of delays. And now we also have intentional use of periodicity. Why? The type of behavior sketched, well, you really need delays. And why do you need delays? If you have no delay, you have ODEs, you can smooth feedback, you can integrate backwards in time and recover the initial condition. But if all things converge to zero, you cannot go back, so you need the delay. But you also need periodicity. Without periodicity, linear time invariant, if there are relevant dynamics, you have characteristic roots, which means exponential solutions, and they do not converge, of course, in a finite time. So you need periodicity and delay to achieve what we achieved. And the potential is that this leads to maybe design methods where you have strong time-bound guarantees needed. Time-bound guarantees are very difficult to achieve with classical methods. Why? Because maybe you can control the asymptotic decay rate, but you cannot control the transient phase. Also, you have called peaking phenomena. If you make the thing faster, maybe we can have higher overshoots and transients. But here we can, at least in theory, guarantee fixed time stability. All right, I'm almost there, just in 5 minutes. One of the main application fields is related to what my colleague and friend Thomas talked about yesterday, applications in vibration control. And maybe let me just sketch some ideas. Input shaping. In fact, we had a demo for an open door day, and there was a crane operator visiting us. And he was positively impressed by the fact that what the controller is doing is what he would do, what he's doing in practice. You have a load, an overhead crane, you want to move it from left to a new set point as fast as possible. What's an operator doing manually? The problem is it should not swing at the end. What do? You first go to an intermediate set point very fast, whoop, and then it starts to swing. You let it overshoot, and when the overshoot is high, then you continue, and it's standing still in the end point. The intermediate thing you can achieve by a filter, because this thing says that we have a shaper. Instead of taking the full step, you take a small step in the beginning, you go halfway, you wait a bit, that's the delay, and then you take the remainder of the step. And that's in fact just a pre-filter. Of course, you can make things more robust by putting the filter inside the control loop, but then you get delays in the dynamics, and then you really have to work with tools like the one implemented in TDS control and discussed before. Another example are absorbers. You have a mass, you have an excitation, and you do not want the mass to vibrate at that frequency. What do? You put there a tuned mass damped system, a so-called resonator, with some active feedback to compensate for the damping, adjust the frequency. And you can do this by delayed feedback. It's also very natural in the context of vibration control because you're tuning phases of signals. Okay, that's the setting, the original setting. We look at non-collocated vibration suppression. Suppose that you cannot put the absorber at the place where you want to eat up the vibrations. So here, this is the target. You do not want the target to vibrate, but you cannot put the absorber on the target. Think about a surgery robot. The target is in fact the cutter, but you cannot put a device on the cutter. You put it elsewhere. In that setting, it's a bit more difficult because now you have to make sure that a whole substructure behaves like one absorber. It means, in fact, that you have to tune parameters of some internal feedback to tune a whole substructure, a whole multi-body problem. But it can even be worse when there is some kind of parallel connection here. Because you know you cannot separate a vibrating part and an absorbing part. And then we designed methods based on spectrum shaping, but also based on shaping zeros. So we work at the same time at the level of poles and zeros. Because at the end we want to have a zero response from the disturbance to the target position at the frequency G omega. And we can do this all with time-delayed feedback and the use of developed software tools. Here you have just an illustration. This is the target here. This is the source of vibrations. And the absorber is somewhere on the left. We cannot attach it to the target, but we attach it to some other mass. And the parallel spring is the one shown here. So now feedback is not active, so the mass is vibrating in the middle, and now it's active and it's standing still. So by acting at one place, we ensure that at another place we absorb vibrations at a given frequency. And the fact that we use time-delayed controllers made it also quite easy to retune when the excitation frequency changes, so to achieve robustness. Anyway, so I talked a lot. I think that you all need a coffee or tea or to have a chat, so I will conclude here. Thank you.